Hello again and welcome back. We are starting our next section in abstract algebra, which is on mathematical induction. Again, all of you have had proofs, so this should be review. The book goes through the principle of mathematical induction, writes that out in terms of the math notation, but we'll also go over this in how you would actually go about using this principle in proofs. And there's also the second principle of mathematical induction, which is slightly different, and we'll work on that one as well. Okay, so let's start off by, let's go ahead and read the first principle of mathematical induction, which is up here. If S is a set of integers containing A and let me edit this a little bit. And if S has the property that if N greater than or equal to A is in S, then N plus 1 is in S, then S contains every integer greater than or equal to A. So this is talking about sets, and as you might imagine, how you actually prove the principle of mathematical induction is using the well-ordering principle. The book doesn't go over that proof, and I'm not going to either. And on the other side of that, I'm also not going to go through we're not typically going to use this version of the principle of mathematical induction in actually proving things. So what I'm going to do instead is talk to you about how induction is typically used in proofs, and then we'll do an example, then we'll move to the second principle of mathematical induction. So, how to use induction in proofs? Well, essentially there are 3 steps. 3 steps. The first one is what we call the base case. And what you do here is you show that N equals 1 has the property in question. And here, I mean property usually in the sense that we're talking about some statement of something that's true about the integers, but rather than what they're talking about in set notation above. Property in question. Okay, let's move this. Okay, so that's our first step. Actually, let's do this again. Our second step is what we call the induction hypothesis. And this one is essentially very easy. All it winds up being is you restate the statement of the proof for a particular n. So essentially here you assume the property holds for some n greater than or equal to 1. Greater than or equal to here, actually. Okay. Let me actually fix that. Greater than or equal to 1. Okay, and finally, what I call the induction step. I think that's standard terminology, but if not, it's fine. The induction step show that the property holds for n plus 1. So, essentially, you want to show whatever it is you're talking about is true for the value n equals 1. In other words, if you've got a formula or whatever, show that if you plug n equals 1 into that formula, it works. Your second step, the induction hypothesis, you want to assume the property holds for some particular n greater than or equal to 1. When I say some particular n, it's still a variable. You're not like labeling it, but you are setting that n and using it later. And then step 3, you want to essentially adjust what you did in step 2 to show that it holds for the property still holds for n plus 1, and then you're done. That's essentially how you use induction in proofs. So what we're going to do with that is look at this theorem. This is the first theorem, or one of the first theorems people usually prove in induction, which is a proof that the sum of the first n squares is given by the formula n times n plus 1 times 2n plus 1 all over 6. Sorry about that. So what you have to do here is just go through your normal steps for induction, i.e. base case, induction hypothesis, induction step. You can even label them out that way and show that each one holds, and then you're done. So what I would like for you all to do is pause the video, go ahead and try to work through this. There are other versions, other formulas like this that are easy to prove by induction, but this is the one I decided to pick today. So go ahead and try to prove this with your with the video paused, and make sure you follow base case, induction hypothesis, induction step, and then I will get back to you after you unpause the video. Okay, if everyone is back, let's actually go ahead and prove this. So remember, we've got 3 steps here. Number 1, base case. That's what we're going to do first. So let's go ahead and do the base case first here. So I'm actually going to write this out by hand. Again, like I did last time, base case. Essentially, you want to let n equal 1 here. So n equals 1. What we get here is the sum of the first n squares. I'm even going to write it out in summation summation notation. So if you write out the first I from I equals 1 to 1, well, there's only one square there. It's 1 squared. And you can also notice, you can also notice if I plug n equals 1 into the other formula, I get 1 times 1 plus 1 times 2 plus 1 all over 6. If I expand that out, I get 1 times 2 times 3 over 6, which works out to be 1. So the base case checks out here. That's the first thing we see. Okay, so hopefully that made sense. That's usually how the base case goes. Now, one word of warning here: if the base case doesn't hold true, induction doesn't work even if the rest of the things are true. So you actually do need to prove the base case. So here we see that we worked out both sides. We get 1 squared equals 1, and so we're done on that part. The next step is, the induction hypothesis, and that's the next one here. Essentially, we're going to more or less usually just restate the question given. So here, induction hypothesis. Okay, so here, let me write this one out. Suppose let's continue here for some n greater than or equal to 1, 1 squared plus 2 squared plus so on up to n squared. Equals, we want to suppose that this equals n times n plus 1 times 2n plus 1. Okay, so that is our why that is our induction hypothesis. Essentially, you're restating the theorem itself here. Now, don't assume here that that you're done at this point, because you're not. This is just part of the proof. So you're supposing this is true for some specific n. You're not saying it's true for all n. And then your next thing we do is the induction step. And here, typically, and this is the part that varies from proof to proof. Those first two are pretty much standard for any induction proof. But this next one, you want to, so in the induction step, you want to go about the process of getting the statement for n plus 1. You want to show that that's true, and how you want to do that is typically use the statement for n that you've already assumed in the induction hypothesis. So let me show you, oops, don't want that. Let me show you how that works here. So here we're going to just say examine and I'm going to do a summation here. I equals 1 to n plus 1 of I squared. Okay, so what we're doing here is we're examining that. So then what we see is 1 squared plus 2 squared plus 3 squared. I don't need, let's forget the 3 there. Plus all the way up to n squared plus n plus 1 squared. We want to figure out what this is. So we're not just plugging this into the formula now. We're using what we found in the induction hypothesis to figure out where we can go from here. So what we found in the induction hypothesis is essentially this part here equals this. So what I can do is replace those first n terms by this fraction that I've got over there. So let's do that. So I have n times n plus 1 times 2n plus 1 over 6. And then we're not done here. Hang on, let's erase that 6. It's not even. we're not done here because remember we only added up the first n squares there to get that. So we also still have n plus 1 squared. Now, we don't know that this is what we want it to be yet, but let's figure out what we want this to be. So here we want n plus 1 times n plus 1 plus 1. That's not room enough there. Sorry. I'm not going to do the steps here. You all can follow them. N plus 1 times n plus 2 times 2n plus 3 all over 6. And essentially what I've done here is just took the original formula that we had and replaced each n by n plus 1. So here we get n plus 1 times n plus 1 plus 1, which is n plus 2, times 2 times the whole quantity, n plus 1 plus 1 gives us 2n plus 3. So here, that's what we've got. We want to add this business up, and or we want to add the things we've got down here, right here. We want to add these things up and get what we have up there. Okay, now, the steps on this can vary from problem to problem. Here, one thing you might not guess, but the thing we want to do here to make this easier for ourselves is factor out an n plus 1 to begin with. So I'm going to go ahead and do that. So I factor out an n plus 1. My first thing becomes now n times, n plus 2. Sorry, not n plus 2. 2n plus 1 over 6. The other term was just n plus 1 squared, so I factor out an n plus 1. I get just n plus 1 there. Okay. So all I've done at this point is factored out an n plus 1. I think I'm going to have to erase that red line there, sorry. Okay. All right. So what we do, let's take a look here. We have right here a sum. One of the things is a fraction, so we need to add fractions. In order to do that, we've got to have a common denominator. So let's go ahead, leave the n plus 1 out front as we had before. I'm going to expand the top of the first fraction, which gives me 2n squared plus n over 6. And then if I multiply and divide this n plus 1 by 6, I get 6n plus 1 over 6. All right, let me make, sorry, not 6n plus 1, hang on. 6n plus 6 over 6. There we go. So all I did there was get a common denominator, expanded the first one. Now, from here, just add the two tops together. Again, leave the n plus 1 here. So I'm going to have 2n squared plus 7n plus 6 over 6. And then, as you might guess, all we need to do is factor the top of this second equation, and if you factor it out, it gives you exactly what you want, which is 2n plus 3 go. That is our proof. Hopefully that makes sense to everybody. Again, you can ask me questions about this if you want. That is our use of induction. Now, our next thing is the second principle of mathematical induction. I'm not going to read out their version here. It's very similar. Let me fix this here. We need an equal to sign there. There we go. Very similar to the first principle, but again, the actual statement isn't what we would typically use to go about making proofs. So what we're going to do instead here is we will actually do something similar to what we did up here, which is that ain't gonna work. No, okay, hang on. There we go. We're going to show the 3 steps like we did before, which are going to be similar, but things are going to be a little bit different. So here you have a couple of things that are going to change. So the thing to notice about the second principle of mathematical induction is you're not guaranteed that n being in S means n plus 1 is in S. What you're required to have here is that all the values up to n, not including n, are in S, then n is in S. And these two are equivalent. You can use one or the other. Either one works. So one thing here, the base case, you do need to show n plus 1 is in S, but sometimes, depending, and I'll use the example I've got below to explain that. So you have to show that n equals 1 has the property in question. And here I'm saying, and sometimes n equals 2, and so on. We'll see that in our example below. And the reason sometimes you need that is if you are using the fact that early values hold this property in the later part of your proof. And so we'll see exactly how that works here. The induction hypothesis is, again, a little bit different. Here we want to show that the property holds for... Come on, let me do this. There we go. For all integers k less than n. So here you're not assuming that this works for n. You're assuming that it works for all integers k less than n. And then, come on, there we go. And then you use that. Usually you have to use at least 1 or 2 instances of values smaller than n to show that the property holds for n. Again, these two are equivalent. If one works, the other works, but sometimes the second one is easier to use, and that's the case in the example that we're going to do here in just a second. Okay, so hopefully that makes sense. Let me look at our theorem that we're going to look at here. This is a theorem about the Fibonacci numbers. Hang on. The subscript there. We have the Fibonacci numbers, f sub n. We define them as follows. The first 2 are 1, and to get any one after that, you add the 2 previous ones. So essentially here, f1 equals f2 equals 1. That's our definition for the first 2 Fibonacci numbers. And for any Fibonacci number after that, try not to get that 4 in there. There we go. any Fibonacci number after that, f sub n plus 1 equals f sub n plus f sub n minus 1. In other words, the two previous Fibonacci numbers you add together to get the next Fibonacci number. And this is just what everybody's familiar with as far as how Fibonacci numbers work. So we are going to do that here, or we're going to use that here, and what we want to prove is that f sub n is always less than 2 to the n. So we want to prove this. So, in this case, we're going to have to use the second principle of induction. So, let's go ahead and let me go ahead and have you all pause the video again. Try to do this one. Remember here, we're going to show, we want to do this roughly the same steps. So show that n equals 1, and maybe more than that, depending, are actually hold the property in question, and then use the induction hypothesis, essentially say that the property works for all integers k, and then show that what you're looking for, f sub n, is less than 2 to the n. So go ahead and pause the video, try to do that. You should be able to at least write out the base case in the induction hypothesis, even if you can't quite get to the induction step. So go ahead, and I'll get back to you as soon as you unpause the video. Okay, if you are back, let's go ahead and start here. Base case. So my base case, I'm actually going to use two of them here, and I'll explain why a little bit later. But here, f sub 1 equals 1 is less than 2 to the 1. That checks out. And we don't know that we're going to need this one yet, so sometimes you might have to adjust this later. F sub 2 also equals 1, which is less than 2 squared, which is 4. The reason we're going to need to use two of them here is just to show that this is going to work when we have n equals 3. Actually, it's probably a little bit overkill. Sometimes I do that here, but, you know, it is what it is. Sorry about that. All right, so, hang on. Induction hypothesis. So let's state this out. So here we want to assume for all k less than n, that f sub k is less than 2 to the k. Okay, so we want to assume for all k less than n. So this induction hypothesis is the part that's a little bit different from the first principle of mathematical induction. The base case is pretty much the same. Like I said, I'm probably doing a little bit of overkill with that second one there, but in any event, the induction hypothesis says, hang on, I need my highlighter, says that for all k less than n, f sub k is less than 2 to the k. So you're making this property a little bit more general than you did previously. And so hopefully you were able to at least get these two steps. Let's go ahead and look at the induction step. So here, I'm going to start this out with a we want to show. So let's do that. We want to show. This part is actually really easy, and second principle of the second principle of induction proof here. So we want to show that. So what we do is we start off with f sub n. So f sub n equals, we know by our rule for the Fibonacci numbers, this is f sub n minus 1 plus f sub n minus 2. So that is from this statement, hang on, right here. Obviously I had to adjust it because we don't have a n plus 1 subscript, but we're adding up the previous two, so we know that is true. And what I have to do now, each of these are less than n, right? So this, sorry, I don't want that color. This n minus 1 and this n minus 2 are both less than n. So what that tells us is our induction hypothesis holds. So that means this f sub n minus 1 is less than 2 to the n minus 1. And f sub n minus 2 is less than 2 to the n minus 2. Let me do the underlines a little bit different here. So here, this first one, I'm going to underline once. The second one, I'm going to underline twice. Essentially, this one here is less than that. The second one is less than the second one. So we know that their sum has to be less than that sum. Now, you'll notice this still isn't what we want. We have 2 to the n minus 1 plus 2 to the n minus 2. We want 2 to the n, so we need to go a little bit further than that. So what we can do here is we can factor out a 2 to the n minus 1 here. So I'm going to use equals here because it's going to, this one is actually going to be equal here. Let's see. So I can factor out 2 to the n minus 1. And if I factor that out, factoring it out of the first one leaves me 1. Out of the second one leaves me 2. You'll notice here, 2 to the n minus 1 divided by 2 to the n minus 1 leaves us a 1 there. And so a 1 here and then a 2 here. Okay. And this, we don't have to do too much more. Sorry about zooming again. Just want to make it legible when I'm done. This has to be less than 2, or sorry, equal to 2 to the n minus 1 times 3, which here, this is the part that's actually kind of a jump. If you don't know that this is what you're doing, it might take a little while to think about this, but we want this to be less than 2 to the, sorry, did I say, yeah, 2 to the, hang on. Yeah, okay. Let me make sure I'm doing this right. Did I make a mistake here? No, okay, I think I'm good. All right, so here we've got, this is 2 to the n minus 1 times, hang on, what did I do wrong? There's something wrong here. Oh. I factored wrong. Okay. So, let's fix this here. Let's erase all this. And why do I have to erase this? Because I was stupid and made a mistake. No. Making a mistake doesn't make you stupid. But I did make a mistake. It happens. So here, let's fix this here. This erase is weird. It's like it erases one dot at a time. Okay, and let's erase over here as well. because here's where I made my mistake. Okay, so I don't need to factor out, I don't need to factor out a 2 to the n minus 1. I need to factor out a 2 to the n minus 2. When I factored it wrong too. So if I factor a 2 to the n minus 2 out of 2 to the n minus 1, that leaves me a 2. 2 to the n minus 2 out of 2 to the n minus 2 leaves us a 1. Essentially here, remember, factoring is just dividing. So here, if I divide 2 to the n minus 1 by 2 to the n minus 2, I subtract the powers, I get 2 to the first. The second one, I get 2 to the 0, which is 1. So there was my mistake. Sorry about that. But, you know, it happens. Even to the incredibly wonderful. All right, so here we get 2 to the n minus 2 times 3, which is almost what we had before. That's an equal to. And this now is less than 2 to the n minus 2 times 4, because 3 is less than 4, and 4 is 2 squared. Let me zoom out. Oh, it zoomed out for me. Whoa, that's not what I wanted to do. Okay, sorry about that. Let me zoom out here. So here you'll see we have 2 to the n minus 2 times 3. 3 is less than 4, so that next step works. The next step says 2 to the n minus 2 times 2 squared, which 2 squared is just 4. Now, if we rearrange this, if we multiply powers, we add the, if we multiply, a power times a power is, we add the powers. So I get 2 to the n, and then if you look at this, we have this whole unbroken chain from, let me use blue here, from f sub n all the way to 2 to the n. Everything in between is either, blue is fine, is either a less than sign or an equal to sign. So that means what you have at the end is less than what you had at the start. So we can actually write that down here. So f sub n less than 2 to the n, and bam. And let's see if I can draw something here. Yeah, he's got to wear a funny jacket, right? Okay, there we go. So, so what we wind up with here is f sub n less than 2 to the n, which is what we were aiming for in the first place. So, there we go. All right, and that is pretty much it for this video. I will answer any questions anybody has. You can email me, contact me on the chat. Anything is fine, and I will talk to you again soon. Bye.